Hey folks, good morning. It's uh, it's an interesting day to say the least. But I'll tell you the agenda of this live stream. It's to read the second part of Memcached. Right? We were just having a live class at Interview Ready, and we had some issues in getting Zoom up, and it doesn't seem to be that it will be resolved quickly. So I'm doing a workaround, which is uh, going live on YouTube. So good morning, good morning. Yes, go on LinkedIn, let's go on Twitter, let's go on what else do we have? Pretty much it. Hey folks, good morning. Let me know what you're thinking. I'll just talk in a few minutes. Others, good morning. Hello. Let's go to the interview ready. Jan, good morning. Arindam, hello. Okay. So let me see if it's set correctly. Awesome. A lot of us are here. And firstly, thank you for joining at almost zero notice. Secondly, if you were currently in the live class at Interview Ready, then this is where we are going to be hosting it for today. Don't worry, we are going to again host it again in Interview Ready. What has happened is a mess up with payments at Zoom. There's for some reason they are no longer being able to take recurring payments through Indian debit cards. So yeah, that's a bit of a problem. So we got knocked out of the what do they call it, meeting in Zoom within 40 minutes, and that's when we had just barely started. We'd just gone through some of the doubts. Nilesh, this is getting recorded too. Yeah, I think YouTube auto records everything, so that's good. That's fine. If you have any questions, please post them in the chat. Right? If you and what I'm going to do, the agenda is pretty clear. We are going to do a white paper reading of Memcached. Right? I'm going to go through this in some serious detail, but there is part one of it which I'm not going to be covering because I've covered it twice at Interview Ready, and I'll do a very brief revision of part one so that you have an idea of what we are talking about. But if you want to see it, then you can check it out at Interview Ready. Right? The reason I'm doing this again, like I said, is because the live class didn't work out at Zoom, so we are using YouTube, and it should be fun. So let me start with sharing my screen, and I will share my entire screen here. Yes, wonderful. Okay, so just before we start, let's look at what we are talking about, what beast we are dealing with. We are dealing with Memcached, and this is an in-memory distributed cache by Facebook. It's an open source project also. Facebook has done a lot for this open source project. It's made many updates. It's sent them back to the parent branch also. But some of the things are very specific to Facebook, which they discuss in the paper. And some are even more specific, which they don't even discuss in the paper. Those are optimizations, right? So basic idea is it's a cache. And what does it do? Here are the things which are a bit different. The first thing is that Facebook wants this cache to be easily usable by its engineers. So high adoption rates should be there across the organization. What do I mean by that? I mean, if you write a piece of code, if you write Linux and nobody uses it, then the project would not have succeeded. If thousands and thousands of engineers are using Linux, that's when you know that this project is reasonably easy to use. Okay. it's not our personal preference. The fact is that thousands of engineers use it, which means that it's probably quite usable. So how do you do that? You can document your code well. You can test your code well so that engineers like using it. But most importantly, you have to make integration with the code as easy as possible. So, for example, you write a cache, right? You write a piece of software, you write a piece of code, and I can show you an example of this right here. So let's say this is Gaurav Sen cache, LLD cache, right? And you'll find it on GitHub. It's there, but there's a reason why nobody uses it. Let's go for low design. This is the GitHub one. We are going to be doing a white paper reading of Memcached. Scaling Memcached at Facebook is the name of the paper. So this is the paper that I'm talking about. I just share this in the chat. We are going to be going through this paper, and the idea is to understand in depth what Facebook did, right, to make Memcached scale. So I have noted down the most important points of this paper, and I'm going to be presenting it to you so that we understand this piece of software in detail. It's a crucial piece of software for Facebook because without it, none of the system is really going to work. Tau, which is a graph database, in-memory graph database, is written over Memcached. Memcached is used by nearly all the systems of Facebook to speed up the queries. You need a caching system, so they use Memcached. Many companies you'll see use Redis for a global distributed cache system. This is Facebook's implementation of it. Okay, coming to the point of why are they using Memcached? Well, everybody needs a cache. The general ideas of a cache are all there. Low latency is one thing. High availability is what they're going for instead of high consistency, which makes sense for a social network in general. So here you see a lot of generalized principles because there are so many clients of Facebook which are using it. So in general, you want high availability. Okay. Read after writes level consistency. This is strictly read after writes, but they try to do the level best with read after writes consistency, which means if I make a change, then I should be able to read that change. If I like a post and I refresh the page, I should be able to see the like still there. But if you refresh the page while I have liked the post, you may not see my like. Okay, so Gaurav gets to see all the changes that he has made, but Sai may not see all the changes that that Gaurav has made. And that's fine. Sai is not expecting to see Gaurav's changes. Sai is expecting to see Sai's changes in real time. Okay, that's the basic idea. Now, coming back to where are we? Yes, we want it to be flexible, which means this is extensible. Okay, this piece of technology can be used by many systems to build on top of. As you see, Tau, which is Facebook's implementation of in-memory database, uses Memcached, so it kind of proves that. And easily usable. Thousands of engineers use this piece of software. It is easily usable. So for high adoption rates, what they have also done is they have created client softwares. If I come to you and say that here's a cache that I have written, and this is Gaurav's cache, 890 people have started, right? They may find it quite nice, but it's a learning project. While Memcached GitHub has 12K stars, and it's a very serious project, right? It's not a learning project, it's a project which goes to prod. And the reason why it is so easy is because if I tell you just go to GitHub and see one of the libraries that they have written in C or Go or Python and use that library to use this cache, then it's very easy for you. While Gaurav's cache only works in Java, right? And that too, you have to go and see the APIs first. So what they have done for high adoptability is introduce this idea of clients, software clients that people can just download into their systems and they can use it to hit APIs efficiently. Instead of you making HTTP API call, you can just call this client, this software which you have downloaded, a library, and that library does the HTTP calling for you. Okay, so that increases adoption rates. People find it easier. Finally, the core problem of this cache, right, is that you need to fetch hundreds of key value pairs simultaneously. Think of Facebook. Think of your homepage in Facebook. You have notifications which are being displayed. You have um, a close friends list. You have the news feed. In the news feed, you have the profiles of the people who have posted in the news feed. You have the popular comments. Those comments will have profiles of the commenter. You have likes and reactions. Maybe somebody liked your post, so that comes in the news feed, and the number of likes and reactions are noted over there. The number of likes in the popular comment. Okay, if somebody has liked your post, you get it as a notification. If somebody has asked you for a friend request, then you will get that separately. Maybe that is over here, friend request. Okay, and the friend request itself will have some profile info. So in this way, a single homepage call to Facebook actually goes and fetches hundreds of items. Okay, and in parallel. So in the 95th percentile, 95 concurrent keys are being fetched, 95 parallel keys. So each there are 95 branches in this tree. You can think of it that way. The other thing is that thousands of items are being fetched. Okay, in general, hundreds of items are fetched together. Yeah, is this making sense? Is it? Are you understanding why we are going for Memcached on Sunday morning? Yes. Okay. So these are the requirements for Facebook Memcached. Just a few things. It is a in-memory thing. It's a cache after all. What happens is when you try to get a value from this cache, it will first check in the cache if it exists. If it doesn't exist, then it goes and picks it up from the database and then sets it in the cache. Who is this? A web server. Okay, so the place where you write your code, the place where your application runs, gets a request from up here, get, delete, set, whatever. It gets this request and it tries to find it in cache, tries to find whether that request exists in cache. If not, then it goes and fetches from the database. And when it does find it in the database, it sets the value in cache. Okay. Is this making sense? Yeah. Okay. So on the other hand, if you're deleting values, then you delete from the cache and you update in the database. If you're deleting, you can delete from the cache and delete in the database also. If you're updating set value, then you just clear it from the cache. Awesome. Okay, let's jump to the part that we are looking to really cover. Okay. We have spoken about a lot of this at Interview Ready, so I'm just not going to go through it again. Point number 10, cascading failure avoidance. Okay. The idea is simple. This is a pretty old paper because of which you will see some simple ideas come up. Now, Facebook is very, very mature as an organization. It's also got very advanced techniques of detecting and remediating errors. Okay. Some of it also uses machine learning, but there is a understanding of root cause analysis at Facebook. We are not going to be going through those techniques because they are not covered in this white paper. This white paper talks about a very simple technique, which is when you detect an error, you have to go and fix it. Okay, it's that simple. What happens usually in startups? You detect an error, an alert is thrown, and then you have to go and fix that error. Okay, so what is that? That is, search for FBAR. This system has been written by I think one person, and you see this is 2011, so it's a pretty old system. The idea is pretty simple. If there is an outage, then figure out how to fix it, and then you go to a job queue and you add those fixes as tasks in a job queue. Initially, you can do this manually, right? Later on, what happens is you want some sort of an admin dashboard which can take care of this, and then you want to automate as much as you can from this process. So you can have a look at this paper, or rather this blog. I'll share it in the comments. That is a simple way to get things done. Apart from that, what is also interesting is while you're remediating this issue, while you're fixing or adding tasks to this queue, it's possible that you have a cascading failure. By the time you're fixed the one issue, the other nodes are already failing. Okay, so if that happens, then what you do is you can use something called a gutter. Okay, the idea is pretty simple. Let me explain it here. You have a system, let's say S1, you have another S2 and S3. Now, what if S2 collapses? We have to take all the requests going to S2 and reroute them to S1 or S3. But then that would increase the load on those systems. So, which could lead to a cascading failure. Yeah. If there were 100 nodes being served here, 100 here, and 100 here, the problem is if S2 goes down, you have to take 50 nodes here and put 50 nodes here. So now they're serving 150 nodes each. If a node can go down at 100 nodes itself, if a node can go down at 100 requests itself, then what's the chance of it going down at 150? It's higher. There's more pressure being put on the node. The latency is likely going to increase. And so there's a chance that this can collapse too. And then all of this pressure goes to S3, which is at 300 now. That S3 node may not be capable of handling 300 requests, and it's also much more likely to collapse. If you don't know about cascading failure, guys, I can direct you to this video. Right, it's explained at interview ready also, but yeah, it's also explained at in YouTube. Right, this is the link. A cascading failure, the basic idea is if there's a set of nodes and one of them collapses, it puts more pressure on the remaining nodes, increasing the chance of their collapse, and it becomes a cascade, like a bookshelf falling on another one and another one, and there's so much pressure on the last bookshelf that there's no way that it can survive. Even if you make it very strong, even if you nail it on the floor, 50 bookshelves will keep falling, and then the last one will collapse. Okay, so that's what a cascading failure is. How does Facebook avoid it for Memcached? It has something called a gutter pool. Okay, a gutter pool is basically, instead of you having S1, S2, S3, you also have another pool of Memcached nodes which are not being used by anybody. So initially you have S1, S2, S3, these pools being used by clients. Eventually what will happen is one of them will collapse. When it has collapsed, you just take all the requests of S2 and route it to a gutter. Okay. Gutter in the sense that when there is overflow of water, it goes into the gutter. So when there's an overflow of requests, it just flows in here. Now S3 and S2, S1 and S3 are not affected. S2 collapsed and everything goes to the gutter. So that's the general idea. It avoids failures. It avoids cascading failures. Right. Also, if S2 does not respond to you, it doesn't need S2 does not respond to you, you reroute the request to gutter. Yeah, something like that. Ashish, is gutter a standby node? You can think of it like that. It's a pool of nodes. It's a set of nodes which by. they're not exactly standby, because when there is a request to a node and the node fails, if there's a request to a cluster and the cluster fails, then it goes to the gutter automatically. So there may be overflow also. It goes there and it reduces client failure rates by 99%. Because if a client fails from getting some data in the cluster that they're supposed to, they just go to the gutter. Okay, and they use the gutter for a while. So that is quite innovative, quite simple, very useful. It's a small set of servers that take over responsibility of failed nodes. 1% of Memcached servers inside a cluster are gutter. 1%, just 1%, but significant. Significant to bring down the failure rates by 99%. Okay. On cache get timeout, the client assumes that server failure and queries gutter. What I said, that in case there's a timeout also, you can go and hit the gutter. Okay, on cache miss, set entry in gutter, which means that the cache value is not set. What we talked about earlier, it's a look aside cache. If you miss an entry in the cache, you set the value. If you hit the entry, then you do nothing. This is normal behavior. That's perfect. That's what you want, right? With the cache, you make cache hits. And finally, if the entries in cache expire, then you do nothing. I mean, you can assume it to be doing nothing. In the white paper, what it's in detail. So the stale data doesn't exist for long in the system after the original server has come back up. The problem with gutter is, which some of you might be thinking already, is that what if this node has some latest value here? Okay, and there is an update. So Gaurav, this is a Facebook system. So Gaurav liked somebody's post. This value is updated in gutter, while the original node that they should have gone to, S2, comes back up, comes back online. Now it goes and picks values from where? The database, right? Is the database consistent? 100%. It should be consistent. But there is a possibility that the database is not consistent. Okay, what do I mean by that? Come back to the original problem of a look aside cache and think about it in terms of a gutter. Okay, look at the first part, a look aside cache. You try to get a value, there's a cache miss. You then go and tell the DB, please update the value. So you say +1 in the DB. Then you come back and get the value of +1. Now it's possible that this DB took the value of +1 and set it in its own local store. But we are talking about clusters here. So in the gutter, your next request goes to the gutter and you say, get me the value of the number of likes. The gutter says, okay, I'll try to get the value. There's a miss. What does it do? It picks up the value. It gets the value from its local database. Remember, it's a cluster. So this database and this database are different. It gets the value, and if this was +1 and it set the value to 20, this is still at 29. Are you seeing that there is a data inconsistency? Yeah. So that is possible. That is possible with a cache system which has a backup, right? So this may not be consistent. Similarly, you may have the gutter updating its database value to 30, and the newer, when this instance comes back up, when the gutter is no longer needed, that time this might be at 29. Is this going to stay at 29 forever? No, it won't, because we have talked about replication. There's a change data capture solution that is used by Facebook called Memcached. I think this is the spelling. Yeah, Memcached, which helps propagate changes across databases. The problem is this change may not have propagated by the time you made this request. So there is a data inconsistency. There is no data loss. Okay, and the data inconsistency is just for a while. Yeah, I don't know how many of you are understanding. Most of you are dropping out, but that's okay. You can go through the recording a little later, and definitely, if you've not gone through the first recording of Memcached at Interview Ready, please go through that. It will really help you understand. Okay, so this is the idea. This is how you avoid cascading failures. Why didn't they go for consistent hashing? Because consistent hashing is great when you have one key that you're trying to get, okay, or a small set of keys. We talked about Facebook's problem, which is getting hundreds of keys concurrently and thousands of items concurrently. So when it comes to Facebook, a single key can account for 20% of the requests to a server. A new server who gets assigned 2 to 3 of these keys is also likely to get overloaded. Okay. So you have a set of nodes and you have the gutter, which is not being used. You initially have these requests being routed here. If this goes down, then it's possible that it's containing really hotkeys. It might send them here, which is definitely going to take this also down. So that's what we talked about in terms of cascading failure. On the other hand, if you just pick up all of these requests and send them to a single place, let's say this was at capacity 100, you send this over here at capacity 100, it's fine. The likelihood of the gutter going down is as much as the previous cluster. Okay, but if you send existing clusters more load, then there's a very high likelihood that they'll collapse. Rahul, thank you for that. Yes, I'm very happy that I'm doing a live too. Okay. Scaling Memcache. This is the part where, I mean, the paper title is Scaling Memcached at Facebook. Let's see how they're actually scaling. One of the things that they mentioned is if you do any kind of naive replication, which is you have a web server, you have Memcache, you have the database also somewhere, and you just add more Memcached nodes, it's not going to help. Okay, because the reason is, up to what point do you continue doing this? Let me know if you have any answers on this. Up to what point do you keep adding more and more nodes? Yeah, the problem with Facebook is that they have so much data that you can't do this firstly in one data center. You can do it in a data center, sorry, but you can't do this. Um, you can't come to a node and say that get me 1,000 different values from 1,000 different servers. It's going to spread out too much. So instead, what you need to do to scale is, any idea? Like, take your time, take a couple of minutes. If you have an idea, let me know. There's some writing here, which you can use. I don't know if it will make sense, but yeah. Okay, there are some doubts here. Will the non-gutter nodes be always in sync, or even those nodes can be put out of sync, like new nodes having stale values? So in sync, or those nodes can be out of sync. Those nodes can be out of sync. Yes, Ashish. They can be out of sync. There is a change data capture solution that we talked about, which is Mexqueel, which helps propagate changes from one cluster to another, but it's not real time. Like, it's really fast, but it's not real time. It is a weird side effect, yes. Some stale values you can get, but the assumption is that when a web server or your application server is sending requests, it's going to be sending them to the same node for the same user. So that is a client side thing, and the client is called mech router in Facebook. So that takes care of sending the same request, sending the same server's request to the same node. Okay, if you haven't checked out consistent hashing, the video in this channel, do check it out. Yes, okay. So in that way, we are able to order all the requests. Okay. Any other questions, guys? Right. Okay. Let's try to see now how they're scaling. When I say scaling, it's very simply adding more nodes to a problem so that you're able to manage more requests. But Facebook in the paper clearly says that having more nodes added naively is not going to help. The reason for that is that every web server is going to be making a big fan out of requests. Okay, so if you add more and more cache nodes, then each of these web servers is going to be hitting possibly all the nodes in the system. So if there is a problem with one memcache node, all the web servers get affected, right? If I go to put it simply, right, if there is a vaccine that you're giving to the public, and that vaccine is being given to everybody. Okay, so you have 3 shots of the vaccine that you need to take. The first shot is given to everybody. The second shot is from a different company and given to everybody. And the third shot is from a different company given to everybody. You know what the problem is? If any one of those shots have a problem, everybody has a problem. So you can instead localize or contain the problem by creating clusters of memcached. You can't naively scale so that all the web servers are connecting with all the memcache servers. You have to cluster them together so that if there is a problem, you can take care of it locally. Okay. Also, the speed of answering queries will be completely varied if you just go on adding more and more nodes in one region. You have to do them, and that's the idea of scaling. The first idea is that you actually need to build clusters. Okay, pretty common idea, I should say, but it's an interesting thought exercise. Like, why do you need it? Okay, if a cluster fails, then it's independent. Better network utilization. So one cluster has one communication channel, right? And if that cluster fails to communicate, then you can focus on that instead of the entire system. It reduces incast congestion. Now, this is interesting. Dropping packets on client because of large simultaneous server responses. Okay, so for example, if all the clients hit a memcache server, the chance of it going down is pretty high. If you reduce the number of clients which can hit a memcache server, the chance of it going down is lesser. Okay, or even the latency is lesser. So the maximum number of clients who can hit a cache is going to be smaller, right? So maximum latency is also reducing. Okay, you can see here that I have written MySQL commit log. This is basically mexqueen, right? Then the request is going to, this database is going to mech router and update memcached. That's also happening. Continuing with the scaling problem, there are regional pools for larger, less frequently accessed objects. Okay, I didn't really understand. Let me read it out and try to understand, then explain, because I have written these points, but this it's like reading your code after a few weeks. I can't remember what the hell this is. So regional pools for larger, less frequently accessed objects. Okay. These pools are not replicated across regions. Objects in this pool are usually infrequently accessed. Okay. If there are objects which are being less frequently used, firstly, wow, you're putting it in a cache, but I guess it makes sense. These pools are not replicated across regions. Okay. Objects here are usually large in size. Okay. That's the reason why you don't want to put them across all the clusters. Objects have been accessed by fewer users. So let me try to take an example. Let's say that there's a regional pool of cricketers in Mumbai, right? This is a Facebook group, let's say. So why would you want to have a regional pool? The argument would be, oh, because most of the people who are accessing this are in Mumbai. So let's put it only in the India cluster, not in multiple clusters. There's no need of replication across clusters for this thing, because everybody who's accessing it is an Indian. So if I put it in the India cluster, that's sufficient. Okay, even if there are some Americans who are accessing it, the latency is acceptable. As a system, it's okay for us to have slow requests for the Americans because there are only two or three um, who are accessing creators in Mumbai. Is it making sense? You have data which makes sense to be highly localized, very similar to CDN solutions, the way that they think. Highly localized data, maybe a lot of data that you have for that one particular group, you don't want to distribute it across the globe. So in those cases, you have something called regional pools. These are not replicated pools. These are not there throughout clusters. They're just for one region. Okay, and if the regional pool goes down, what happens? It's okay. Spin up another instance, get all that data from a database, and fill that regional pool. Okay, so this is an optimization. It's not about scaling as much. It's an optimization. The first one was about an architectural decision for scaling, which is clustering. Okay, point number 13, cold cluster warm up. This is something that we were talking about in the live class before we had to unceremoniously shut it down, but it'll come back up. Cold cluster warm up basically means that when you're spinning up a new instance, that instance has no data, right? It's a cache. There are no GET requests on it yet. So all the initial GET requests will fail. It'll go hit the DB and then start warming the cache. So instead of us doing that, which is going to take time, one of the things we can do is we can auto populate this cache, eagerly populate the cache, right? So that later on when requests come, we can answer them comfortably. So we can replicate data from a warm cache, a cache which already exists, right? We can take that data and start copying it onto this new cache. So instead of hitting the DB, hit a warm clusters memcache. This is done by mecrouter. Mecrouter, like we said, is something which routes requests for you. So the client that you have goes and hits mecrouter. Mecrouter makes sure that the request is sent to the right node. Okay, there is one edge case when you're trying to warm up a cache. It's possible that there is a database update, right? Anytime there's a looker side cache, it's possible that the database and the cache are not in sync. So you go and get a value from a warm cache. Let's take it step by step. Set k equal to 10 in the database. Then you get the value of k from the warm cache. K is still equal to 5. It's possible. It's possible that the cache entry here is stale. And so k is equal to 5 and it is going to be an indefinitely stale value despite you making an write of k equal to 10. Set value of k equal to 10. Okay. Is it making sense? Initially, you have a value of k equal to 5 in your database. Somebody comes and says, upgrade the value of k. You say, okay, I'll make it k equal to 10. At the same time, you notice that your cache has no entries. So you say, dude, instead of me getting the values from the database, let me use the strategy of pulling warm data from an existing cache. So you go to the cache and you say, do you have entries? And it says, yeah, I have the value of k. What's the value? 5. Sure, give me the value. This was so dumb from my side, right? I just made an update of k equal to 10, and yet when I pulled out warm data of k from a different cache, I got k equal to 5 because it was inconsistent. It had still not pulled the data from the database. So this is the problem. And the solution for this is you basically have something called a lease or a probation time, where when you set the value k equal to 10 and you get the value k equal to 5, you look at the timestamp of this last update. Okay, and if the timestamp is lesser than what you have in your hand, then you say, okay, I won't do it. I won't make an update. What Facebook is using is probation, which means that in 2 seconds, it's expecting the database updates to propagate to the warm cluster. So it doesn't pull data of k equal to 5. It waits for a few seconds after an update and then pulls data. So it expects always consistent data. Okay, but it expects there is a edge case that you can fail. It's possible that they invalidate may come after 2 seconds. And then you'll have indefinitely stale cache, which is the initial problem. Okay. Okay, I know that this is an involved paper, and most of you, especially from college, you shouldn't probably even see it because it's pretty involved. If you're an experienced engineer, and if you like distributed systems, this is for you. So let's continue. Okay, let's also see up to what point we can pick this. From number 14, we went straight to number 16. That is odd. Have I missed a point somewhere? Okay, we are in the last 3 points. Let's go over them carefully. Cross cluster consistency. So, like we said, because it's a look-aside cache, there are many instances when things go wrong or there is a data inconsistency. Data inconsistency is not that big a problem for Facebook unless it is infinitely inconsistent. Okay, that is one problem. Or there is a serious availability issue being caused by it. Okay, so yeah, it's written over here, infinite inconsistency. The previous problem also that we talked about was an infinite inconsistency. Okay, so let's go through this scenario. Number one, you write a value of k equal to 10 in the primary database that you have. Then you delete from cache because you just made an update. We write to a database and we delete from cache. Number three, someone says get a value from the cache. Number four, read the value. You miss. Yeah. Number five, read the value k equal to 5. But the problem is you had a value that you set here equal to 10, which it got replicated, but it was too slow. Okay, take your time. You're now thinking of multiple clusters, not just of multiple nodes, right? Multiple clusters, having multiple databases and multiple caches. First thing that you do is go and try to set a value in the cache. So you delete an entry from cache and then you write the value to DB. That is part one and two, right? Then what you do is from a different web server, from a different one, you try to do the same thing. You try to get the value. So you read the value, you miss it, you set the value. Okay. This is what happened in the cache. And when you read the value, you got k equal to 5. Is that making sense? You basically read an inconsistent value. So what happens here is similar to what we did earlier. We have something called a remote marker. We were talking about a lease time or probation time. So wait for 2 seconds, wait for 3 seconds. Similarly, you have a solution here, which is a remote marker. This is like a version, like a timestamp that I made the latest value at this time. So coming back to the original scenario, set a remote marker on k, then write, then replicate, then remove the remote marker. And in this case, in the memcached, k is deleted. So here, when you saw that a value is being read and a value is being set, firstly, guys, before I go any further, since this is complex, how many of you are understanding? Just give me a hi or give me a thumbs up in the chat. Remote marker, yes, of course. So any other thing apart from remote marker? Is it making sense? Okay, Ashish, crab god. Okay, cool. So let me go over this step by step, right? Is the initial problem making sense. I'll just go over that again. You have two web servers, they're getting requests in parallel. Okay. They are trying to do a write on a database, the and then deleting from cache because it's a look aside cache. Wonderful. Till now, everything is going fine. In parallel, you get a get request from a web server. It says, let me try to read the value. It got deleted. 2 happened before 4. What then happens is you try to read the value from the DB. The DB has values of k equal to 5 because till now the replication has not happened of write 1 to this database. So you read the value of k equal to 5. Now there's a MySQL bin log which goes all the way to this database, comes all the way here. And then there is a setting of k equal to 5 because it read the value k equal to 5 and then it sets it, right? If you do a cache miss, you read from DB and then you set the value in cache. That's what it did. So this is an infinite consistency. It never gets updated. The way to fix this is something called a remote marker, which is interesting. Look at this. Initially, you set a remote marker on k when you are making a set call. Initially, we did a write over here. This is a set. So we did the same thing here, but we also set a remote marker. Okay. (2.1) get k. Okay, where is it going? Where is the get value going? It's going to the memcached. It sees that memcached does not have this value. Okay, so it does a get from the database. Till now, everything is making sense because we set a remote marker on memcached and we deleted the value, and then we try to write to the database. Here we in parallel got these 3 requests, which is try to get the value of k. Now you're going to get a stale value from memcached, but that is totally fine. That is not the problem. The stale value is not the problem. Infinitely inconsistent value is a problem. Okay, so how is this being avoided? When you got a value from the US database, you will then try to set it in memcached as this web server, right? Initially you got get, there's a miss with a remote marker. You are going to try to set the value in memcached. Instead, if you see that k has a remote marker, you decide not to set it. Yeah. Earlier, what was the problem? The problem was that you were setting a stale value in cache as an application server. That was the problem. Now, you're not going to even try to set a value if you see a remote marker. That's it. So think of it in a with an example. I come to a restaurant, right? I say that please book this table for me, and they say okay, the table is booked. Now someone else comes and says, I want to sit on this table, and they say no, this table is already reserved. That is exactly what is happening with a remote marker. A remote marker is coming saying that I am updating a value in cache. Please don't set it now. I have deleted the entry here. I have cleared the table here, and I am putting a reserved over here. Till the people come, till the data comes from the US database, I will not allow anybody else to set the value. Okay, so application servers cannot set the value. This is only to be set by the Memcached change data capture. Exactly, Ashish. Yes. So this is like a reservation thing. It's called a remote marker because a remote database is setting it. But you can say a reserved marker, whatever you like to call it. Think of it as a table that has to be reserved. Nobody else can set it on Memcached except the database itself. Okay. Here we trade latency for consistency, which is fine. Low latency, yes, that is what it is. You could get inconsistent value, right? You could get inconsistent value. We couldn't still stop a person reading k equal to 5, but that's okay. It's inconsistent, it's okay. Infinite inconsistency is a problem, right? We're going for eventual consistency. And this is low latency because we don't have to wait on the remote marker to come through. We can get a stale value. It's okay. We know that it's not infinitely stale. That's important. Okay, there is one edge case here. If you have concurrent updates, the remote marker may be deleted. As you see, when the update comes here, a remote marker is deleted on K. So if you have two people updating K, that's an interesting problem. If you have two people updating K, you set a remote marker on K. The second person also comes, says remote marker, please set it on K. So two people said, please reserve this table. Now the first person comes who has a reservation slip and says, I want to sit here. You say, oh, very good. You remove the reservation. Now what happens? Now anyone can come and update that table, right? The second person's reservation didn't get counted. So what's happened is they just pretty much let it go. They trade off edge case consistency for ease of operation. So after the first write, before the second write is replicated, we delete the existing remote marker, leading to original problem. That is possible. But they are like, okay, Facebook said this is okay. Infinite inconsistency is okay in such a edge case, right? In your restaurant, like I said, there was a reserved table. Somebody called up, said, please reserve this table. Another person called up, said, reserve the same table. You can add intelligence saying that no, that table is already reserved, but you're not. You just have one remote marker per key. So if somebody has reserved it and somebody removes the reservation thing, then everybody's is removed. Okay. In that case, transaction would be successful. In bank, this is not a bank system, Gaurav, but yeah, you're right. In that case, there is a problem. Inconsistency is possible here. If you want to do transactions, you can do it differently. You don't need to do it through a cache. Transactions are usually managed by a separate system which is built for transactions. So you'll have high consistency there. Or you can write wrappers around this database, cache, but still. Okay, we are pretty much at the final two pieces. This is covered at interview ready. Timer wheel for transient items. If you have a circular buffer of linked lists, right? After every second, the buffer current. This is pointer, so I've taken P and put it here, pointing to the wrong place. Every second, the buffer current pointer is moved forward and the current linked list is deleted. This is an algorithm. Timer wheel is something you can search on Google, right? If you want an explanation, then I'll just share it with you here. It's an interesting algorithm used mainly for rate limiting. Facebook is using it for caching. I think our caches have to be updated. This is taking more time than usual. Ours is also an in-memory cache at interview ready, right? So I'll just wait for it to come up. Yeah, it's come up. Okay. Courses, design. Fundamentals, rate limiting. Should be a timer wheel somewhere here. Yeah. So this is a place where you can check out timer wheel. Of course, it's an algorithm, so you can check it out anywhere. But a video explanation is here. So if you have short-lived keys, then you just cyclically keep going forward. Okay, that is something you can do. For example, you have a live event, and comments are something that go out in a cycle. So latest comments right now is here. Latest comments next time will be moving forward in the timer wheel, and you go all around in a circle. When you finish the circle, you are 6 seconds behind or 1 minute behind. So 1 minute old comments are no longer latest comments by any stretch of imagination. You knock them all out and you start adding the latest comments here. So it's a circular linked list. Okay, that's a caching strategy you can use. Final point, which is adaptive memory slabs. This is very, very involved. And so I would recommend reading the paper also, even after you have gone through this. The basic idea is different parts of the cache behave in different ways. Some are long-lived, some are large objects, So what you want to do is you want to create different memory slabs for each object. If I tell you that every object in memory is going to take 1025 bytes or 2048 bytes or 61 kb, then the problem is small objects will still take up 61 kb. Large objects will need multiple 61 kb blocks to be put. So this is not an efficient use of the cache, because when you do a get operation, you have a lot of space hanging around for small objects, and for large objects there's going to be that is still fine, but for large objects also you have to get different chunks from different places and then aggregate them. So instead what you can do is you can have a variable size block. Okay, this was actually spoken by Mark Zuckerberg in the tech talk that he gave for Memcached. Very interesting. He talked about one of the engineers who came up with this idea that instead of having fixed size block, you can have variable size blocks, and that way you can dump a lot more objects into cache. So small objects, all of them will have small uh, blocks, and the large objects will have large blocks. The benefit is you can put more objects in cache. Your scaling is better because you have fewer nodes holding a lot more data. Okay, so it is typical to get a memory slab of factor of 2, but it doesn't really work well for cache objects, because think of it, if you have 32 bytes, the next one is 64, the next one is 128, the next one is 256. So that's not how real world objects work, right? You have slightly larger objects, slightly smaller objects. So instead what they did is they made a factor instead of 2, they made it, I think, 1.1. Yeah, Zuckerberg had said 1.1, initially 1.3, then they changed it to 1.07. It became even more fine-grained slabs of objects. So the first one, if you say, is 100 bytes, another slab will be there 107 bytes, another slab will be there roughly 115 bytes, and so on. So different size of objects can go to the writes block. Okay, and then they said that there are some benefits of this 107, because from 64 you can almost go perfectly to 128 and all the way to 1 MB. So yeah, small chunks, large chunks. The same 1 MB can take 16,000 chunks. The same 1 MB can take one also, depending on the size. And it's a LRU cache, so it evicts items from the slab if it can't find a free slab for that object. So let's say you have 1,000. Let's say you have 16,000 small chunks and one large chunk, and you get one large object. So it's not like you're going to take the 60,000 small chunks and fit that large object in, even if these are free. Okay, you're just going to look for one large chunk. If that large chunk is already populated, you're going to evict and then add the new chunk. So they are like mini caches inside the big cache. You can think of it that way. LRU for each slab type. There is a problem if the workloads change, the current slab assignments will be poorly suited to incoming data. Let's say you have Black Friday, and so the kind of data that you're getting is very different from what happens normally. So the slabs you have chosen are not meaningful for the next 3-4 days. So what's the solution for this? If a slab class runs out of memory and it's evicted, then the 20% more recent than the average of all other classes least recently used item. It means that this class is more useful than many others. So we absorb the having the least recently used item in this needy class. Okay. Let me break down the algorithm here. Let's say you are seeing a lot of objects of size 1 MB being used, and the 64 kilobyte objects are not being used, or 64 byte objects are not being used at all. So what ends up happening is, when you say something is being evicted from cache, it obviously means that there was a need for eviction. There was a need for more objects in this slab. So what you do then is you say, okay, I'm going to expand this slab. I'm going to add more objects for this 1 MB size slab, right? So maybe you had 5 1 MB objects. Now you're going to allow 6 1 MB objects. How are you going to do this? You need to find space for the 6th 1 MB object. You go to the least recently used slab. Okay, least recently used type of object, you go there and you remove some memory from it. Okay, and you take that memory and give it to this most recently used slab. I hope that made sense. I'll just draw it out so that it's sensible. 1 MB, 1 MB, 1 MB, 1 MB. Yeah, you have these 5 objects here, and you have this other slab which is like really small objects. Okay, you come here and you say, I need another 1 MB object. It says, my God, I don't have that much space. Okay, we'll evict. So we evict this entry and we add a new 1 MB object here, which is basically the size of the slab remained the same. But when you added the 1 MB object, you obviously knew that this slab is being used, recently used. So you go to the other slabs. Maybe there is another slab which is like really big objects. You go to the other slabs and you say, which one of you was least recently used? So this says I was used at 9 a.m. This says I was used at 10 a.m. Ah, you were recently used. You were not recently used. You're not that important. So what we are going to do is we are going to take 1 MB out of you and give it to this slab. Okay, so now this, instead of having 5 MB, has 6 MB. 1 MB slab got added, another one, with the hope that this is the kind of objects we're dealing with. And this initially had 5 MB. This entire space is 5 MB. Now it only has 4 because it was least recently used. Yeah, so that's the idea. So it's adaptable. The memory slabs are adaptable. You may think, who cares? I mean, you can populate the cache much more effectively if you're thinking about the memory slabs that you're going to use per object. So if small objects are no longer being used, then get rid of them. If large objects are no longer being used, get rid of them. It's okay. And so what will happen is after this update, maybe you see that this becomes a 11 a.m. thing. So if you need space here, you start chopping off objects from this place because it's 10 a.m. Least recently used. Okay. Right. So we absorb the chunk. I'm the least recently used. Cool. Thanks, Arpit. Yash is asking, I'm really interested in system design. Where to start? I'm working, so can't dedicate major chunk of day to it. So if you're interested in learning system design from scratch, we have interview ready. You're currently working, right? So it makes sense for you to invest in this. I think it's the best course out there by far. Otherwise, I wouldn't be selling it. But this is a course by me, interview ready. If you're looking for the absolute basics, also it is there. Yeah, it's all there in prerequisites. So go to the basics. You can start here. This is fundamentals. This is the basics. Monoliths versus microservices, horizontal scaling. So this is something that you can go for. YouTube videos, which are then the prerequisites. All the videos which are a little more advanced are in the paid sections. Okay, so you can watch this freely on YouTube. Here it is better structured, and there are discussions and resource links, okay, which you might want to go through. Even on YouTube, I have the resource links somewhere or the other, but this is a bit better structured because I can tell you exactly what you need to do one after another. A playlist also works that way, but it's much better broken down over here, right? In YouTube, if you don't put a 10-minute video, at least it won't get noted only by YouTube. The algorithm kind of forces you to do things. Here, there is no forcing. Here, everything is put in the right way that I want. Yeah, so APIs, message queues, these are all the basics. You can go through this. But then if you go through fundamentals, then yes, we start with a deep dive of databases, rate limiting, consistency, caches, networks, replication, migrations, security. This is more on hashing, trade-offs, consensus with Paxos, and observability. This is pretty recent. Okay, and then you have high-level design, different chapters for that. For example, cab aggregator like Uber, and machine coding. Okay, machine coding is pretty involved. Uh, some good news, guys. 17th, as is evidenced by uh, the launch date, we'll have low-level design chapters being added here. A lot of them, solid principles, design patterns. A lot of low-level design content is coming. Yes, there is doubt solving for paid users. Ashish, you can. So, for example, I don't think it's a doubt. Right? Pie chart is a little confusing at first. So here's a comment from Gaurav which helped understand it better. What's going on? Why? Agree, I believe that load balancing. Okay. This is the basic start. If there is no cache, you can see that these are being answered. You can post the comment in the discussions. We look into the comments, of course. Another one example would be here. This is a high level design. So let's go through. Yeah, there's a question. What you described here is not JWT token. Okay, this is me saying that this point makes sense. Okay, we set predefine expiry y to maintain auth. Okay, yeah, doubts are answered here. Discussion tab, doubts are answered. Apart from this, you have live classes twice a month. So that is where some doubts are answered. But now we have gone into white paper readings. So we are going through these white papers as you saw today. Right, I was not able to do it because of Zoom. So I'll have that sorted. But otherwise, we have white paper readings planned for the next few months. Okay, next one is going to be Tau. Tau is a graph database by Facebook. And then you have Zanzibar, which is Google's authentication system. And you also have Google Monarch, which is Google's time series database. And then just to compare it with Facebook, has its own time series database called Gorilla. So that's also an in-memory time series database backed by Influx DB. No, sorry, OpenTSDB. Yeah. So that's the idea. Yeah, if you have doubts, yeah, you can ask them always. Okay, I think that's it. That was Memcached from Facebook. Okay, if you have come from the live class, so sorry for making you go through two portals, two platforms. We'll do a revision of this next time so that we truly understand it well. And thank you for tuning in, guys. Thank you for making this fun Sunday morning. I'll see you next time. Have a great day. I'm ending the stream. Bye bye. But it really feels good to just connect with you from time to time, and uh, I'm so privileged actually to be able to talk to you about technology and learn it myself, and then just explain it. And I'm sorry sometimes that in case I don't explain it the best way that I possibly can. But these papers are quite involved, and to go through them, take down the points, and remember all of it, keep it in memory is interesting in itself. So thank you for being in this journey. Please do more live classes like this. Yes, Crabgot, thank you for coming. And Ashish, thank you for, yes, the questions were amazing. And, Sunday is fruitful for me too. Himanshu, ask them in the comments. I'm sure somebody can help you out, right? It's, yeah, Hussein, go ahead. Of course. Last question. What is the last question? You can also post it in the comments. Thank you, everyone, for coming, and have a great day. Take care of yourselves. Bye-bye.